So this title should really have a question mark here. Invention as cultural accumulation, and is there evidence from patenting about that phenomenon that we call cultural accumulation? And I'm going to go through a little bit the conceptual background behind what motivates this research. So I'm going to start with explaining the position that we're going to take in this research. We're not going to endorse the thesis that it's individuals that invent, and I think most of us agree on that, right? It's not the individual genius that invents. But I'm also not going to endorse the idea that it's individuals within populations that invent, which is the, I think, most prevalent picture that we have of invention. Instead, I'm going to say that it's populations themselves that invent. And you may wonder, okay, but what do you mean by that? What's the difference? And I'm going to say that, and you're going to hear it in the words. So I could say that here, the individual is inventing through his own individual learning. The individual here is inventing through some sort of social learning. So he's in the middle of some sort of information pathways that allow her to invent. Here is just invention as collective learning. And the idea here is that the inventor is like almost the tip of the iceberg, is the perhaps the least important part of this. I have other work where I argue that it's actually the most important part, but for this project, I think it's perhaps the least important part. But the idea, I think, is very well summarized in this sentence that I've heard Robert Boyd said several times, is that invention is the act of standing on the shoulders of midgets, because it's like we're right, it's inspired by Newton's phrase, but he emphasizes the midgets here because it's not like three other geniuses that I'm standing on, but it's hordes and herds of little contributions of the population you belong to. But what's the difference? I mean, yeah, this person here who was the tip of the iceberg in one single contribution, what is the difference between that and this one? And I'm gonna highlight a few possible differences that may have different implications when we want to quantify these things. One is that in social learning, there's a lot of emphasis on the horizontal transmission of information. So you learn from peers. And so there's a lot of talk about spillovers. And both in the economics literature, but also in the psychology and the anthropology literature, you talk really, you say that this is social learning. And social learning is the process by which an individual learns, but within a social context. Here in collective learning, maybe you want to emphasize the vertical transmission. So it's the transmission of information across generations. And it's not so much that any individual is learning, it's just that there's a transmission of information, and that accurate transmission of information allows for the accumulation of collective know-how. It emphasizes cooperation between individuals, so you need to have then, therefore, complementarities between what people know how to do, which leads to the idea of division of labor and expertise and the coordination of that expertise. And notice that I don't think this is really clear here. You can add as elements in the social learning paradigm. But I think if you want to understand collective learning as something that is very specific of the collective and not of the individual, I think these are useful notions. This has been, I think, at least in the type of fields I work and read, most been thought in the field of cultural evolution. I don't see it as much in economics, And so cultural evolution has, I've read these two strands where they emphasize social learning, but there's some strand that emphasize the collective learning aspect. And this is a nice sentence from this paper that I like a lot, that I'm just gonna read to you. It's, they say, just as thoughts are an emergent property of individual neurons, firing in our neural networks, innovations, and here they don't distinguish between innovation and invention, so you could say inventions, arise as an emergent consequence of our species psychology applied within our societies and social networks. So these can produce complex designs without the need for a designer. And here the emphasis on without a designer is again emphasizing that maybe the inventor is not that important, is rather the population. One of the things that we do know, and I'm not gonna show work on this, is that there are meaningful ways in which you can think of collective know-how different than the know-how that a collective of individuals, that the sum of the know-how of individuals, there's a meaningful branch or of papers that take this idea seriously and actually show that it explains very well the differences in wealth across countries, cities, and I've done work myself in taking this idea seriously to explain why there is urban scaling. So there are pieces of evidence that may prove this paradigm at least useful, a useful different approach. So the research question here for us, and this is a project again with Jose and Debbie, it's a very simple one, is, okay, this is the time series of the accumulation of patents in the patent record. This what I'm gonna analyze is tiny data. It's not even small data, it's not even data, small data, this is tiny data, it's just, I don't know, how many, a little bit more than 200 points. This is all what I'm gonna be analyzing. And the question is this collective learning, as we've been discussing, right? Or is just a trivial process of accumulation in a historical record? It's just throwing things into a bag independently, and these things accumulate and they grow, and you know, population size is growing at the same time, so why not? A set of related questions. Should there be a distinct quantitative signal for collective learning in that time series? How actually do we measure collective know-how? What would be a good proxy for that? Are patents that proxy? If we had a measure, if we said, okay, I can deal with that measure, why and how would it grow? And what would be, I would like to know, what would be the specific function, if there is a specific functional form, and which specific functional form there would be for such a process? Those are the related questions. And the answer may be no for everything, right? And I'm gonna show you some evidence in favor, some evidence against, and some inconclusive evidence. So let's start with know-how. I'm gonna say that know-how is the number of things you know how to do. And this is something that is actually common, right? We ask people, how many languages do you know how to speak? How many different mathematical problems do you know how to solve? How many cooking recipes do you know how to cook? And so on. And that's a proxy for how much that person knows about a certain topic. And if you open up for different topics, then it's also a measure for how much a person knows. And so given that, I would posit that collective know-how is the number of things a collective know-how to do. But then you can see that here is you face a little bit, this is already problematic. Because in a society where what the collective knows how to do, if you count, okay, how many technologies and things this society knows how to do, and all those things are things that each individual knows how to do, then what's the answer for what's the collective know-how of that population? I mean, it wouldn't make sense, right? I would claim that there is no collective know-how if everyone in the population, each individual knows how to do everything that everyone in the population knows how to do. But to maybe refine this definition, let's think about what would be collective learning. And I will posit that it is increases in collective know-how that are not accounted by increases in individual know-how. And you can say, but what does that mean? So one way is to think, well, instead of thinking of increasing the educational attainment of everyone in the room, you actually divide labor. You create expertise. Another way, and it's one of the ways we studied it a lot at the center where I work in, it's that it's the immigration of foreigners. Foreigners bring know-how that is different from the one that is already in the society. If you can coordinate that new know-how, then you increase the collective know-how of the population without increasing the average know-how of any individual, right? So these are ways of thinking and making tangible these definitions. So I'm going to add to this definition that collective know-how is the number of things that collective know-how to do that no individual would know how to do. And so that brings me to your question a little bit, because yeah, I can maybe understand the transistor, but would you ever be able to do it from scratch? No. So it's obvious, and we know this, right? We know that a lot of what we do, what we have in society is cumulative know-how. Anyway, so all this rambling leads me to the following conclusion, that operational set of a starting point that I can start working with, which is that know-how is the size of a set, and this is not something new. We're far from the first to suggest this. This person has worked a lot on that perspective, and the question is whether we can say that whether it's trivial or non-trivial, in what sense. And I'm going to be using right now and that's the language that many of the anthropologists use. It's a process of accumulation. And so I'm going to use these terms interchangeably. Culture, for them, is not this fuzzy, nebulous thing that you cannot define around you, that defines your identity. It's not that. It's the body of collective know-how in your society. And it can be counted. It can be quantified. Proxies are just counting toolkits but also practices, beliefs. So you can characterize according to them a society, very crudely, of course, as a vector of zeros and ones. And you can compare these vectors, you can quantify them, and so on. And so a cultural trait is just one element in that vector. And it's typically thought as a distinct technology. And a technology is not a flashy object. It can be a practice. It can be a way of speaking. It can be a way of relating to your neighbor. And cultural accumulation is, for them, collective learning. So it's a process of accumulation. It's the expansion of a set. Now, that has some sort of obvious implications, but I'm going to state them. I'm going to state the obvious, and this has been implicit or explicit in all your talks and and what you've said, but it's better to be explicit about this, because this will take me to a specific testable hypothesis, which is that if invention is a process of cultural accumulation, there will be path dependency, and past and present inventions will affect future inventions permanently, right? So this is, for example, one of the diagrams in this paper here by Enquist et al. In 2011, modeling the evolution of diversity of cumulative culture, where they make a taxonomy of different events that can happen. And so this is the state, this is the set of cultural traits in the society, and these X and Y's are elements. And they try to study what would be the effects if there are traits that hinder or foster further accumulation of other traits. So what happens at a given point in time, if you acquire one of these traits, it may have repercussions on the future on how you keep accumulating things. So the research question now restated is, are patents an instance of cultural accumulation, right? Meaning that, are they affected by previous inventions? And I think we will all agree that they are, but I want to be very explicit about why I am asking that question. It's path dependent, non-stationary, self-propelled, right? Cultural evolution. I'm going to say that cultural evolution or collective learning is a process of accumulation that is self-propelled. so what are going to be the hypotheses? If accumulation of patents is not cultural, but determined by independent contributions, the time series of patents should lack a unit root. So economists will know by heart this notion, but I'm gonna, for those of you who either don't know or have forgotten, I'm gonna review it very quickly. Another way to understand where this is taking us is to sort of negate the hypothesis, which is that if accumulation is cultural, the time series of patents should display some sort of memory. So unit root is related to memory in a time series. So let me show you the results, and I'm gonna use then again, as I said, the patent record, the number of patents accumulated from 1840 to 2015. This is not a unit root process. This is just random additions, right? So no single point depends on the ones that came before or the ones that come next. They don't affect each other. This is just a stationary process of random variables. This one is the unit root process, where there was a huge shock, and that shock shifted the whole series permanently up. And but this is an you may think, oh, so there's like trends in unit root series. Not necessarily, right? So this is a time series with a trend, but that doesn't have a unit root. And so one of the properties of unit roots is that they converge back to a trend they had before. And this is just a simple toy equation for this. This is a simple toy equation for a unit root process. The term unit comes from the fact that this coefficient here is a 1. And this is not a unit root process. It doesn't depend on previous events, but it may have a trend. Okay, so we're going to be trying to see for this type of processes. Now, this is restating what I said. Okay, so these are the time series that I'm going to be looking for, that I'm going to be studying. This was the original one that I showed you. The other one that I'm going to be analyzing is the logarithm of this one. And then I'm going to be taking, notice here that if I take first difference here, I come back to this point, okay? So this is a way of understanding at which point should I observe or stop observing a unit root process. So that's why now from here to here, I just take differences from year to year. This is obviously the new patents added each year. The differences in here can be interpreted as the rate of change. And then I take, again, differences here. So the differences in the new patents each year and the differences between the rates of change in each year. Okay. And I'm gonna, these things here are these tests that I'm gonna use to test the hypothesis of the unit root. So the ADF, the augmented Dickey-Fuller test, tests for unit root. The null hypothesis are unit root. And but one of the things that people know is that it's very easy not to reject this test. So actually what you want is to reject it. Get to a point where you can reject it, because that's the part that is harder, right? It's harder to find that process that is completely stationary. So I want to reject this thing. Conversely, this KPSS test trends stationarity. So I want to not reject this. I want a process where there is some sort of trend stationarity, and I'm rejecting the unit root process. Here, this is exactly what I don't want. I rejected trend stationarity, but I didn't reject unit root. So this is kind of uninteresting from the point of view of my hypothesis. The same here, the same here, the same here, the same here, right? You understand that I put a dot here because I was able to reject at a 1% level this test. But interestingly here, I also reject the unit root process. So this starts to feel like a stationary process. But this one is better. This one, I can reject the unit root process, and I cannot reject that this is a stationary, trans-stationary process. Okay, so let's go backward. This means that this quantity is stationary. This is the quantity that is sort of coming independently. It's sort of noise that comes independently. These are the contributions that are sort of independent. But if you break that apart, then you get to here. This is the unit root process. This, or there's evidence, right? I cannot prove it, but there's evidence that there's unit root process here. There's this funny period between up until 1900 that is interesting. We can then, this is the same thing that I was saying, we can test instead since 1900 to 2015 what was happening, and you get the same story. And this is a typical time series of a unit root process, right? All right, so what are the implications? I would claim that the system has memory and has like some sort of long-term memory because I had to take differences twice. Since I had to take the differences in the logarithmic space, it means that the shocks that permanently shift the time series are multiplicative. I'm not sure if that's relevant. That may not be relevant, but I think I have a tendency to think that when I hear multiplicative, there's some collective, there are some collective processes going on. I have that prejudice, but I would like to hear your thoughts about that. But the question is, does this stand as a sufficient or necessary piece of evidence for cultural accumulation? I don't know. I would like to take seriously the counterpoint as well. But let's look now, a unit root process can still be consistent with a deterministic component. So you can have, a unit root process is the combination of two things, the unit root, but also a deterministic component. So I want to understand also the deterministic component because you see that these time series are very stable at the aggregate. So I would like to have a model for that as well. We already have evidence that the contingent aspect of patterns seems to be consistent with a process of cultural accumulation. And so the question now I'm going to try to study is, what about the deterministic component? For that, okay, back to the drawing board. I have these two series, the accumulation of patents. This is the new patents per year. If you ask me, just like that, what type of growth is this? I think many of us would say, that looks like exponential growth. But exponential growth means that if you take logarithms of this axis, you get a linear trend. And you already know the answer, we don't see that. We see a roughly sub-exponential growth. Interesting, because many of the comments that I get when I talk about this is that, yeah, of course, I mean, population size is increasing, right? So population size is increasing exponentially. This is driven by population size. Well, if you take into account population, then this becomes even more puzzling. So another way of looking at exponential growth is through this equation. So maybe if cultural accumulation, if patenting is cultural accumulation, is a process called adaptive learning, we shouldn't be measuring time in years. We should be measuring time in the number of items that I have already accumulated before, right? So I should be plotting this against this, not against time. So I'm going to do that. Because in other words, yeah, that's what it is. New patents may not be a function of time, but of the number of accumulated patents. So this is what I do here. So this is the accumulated patents so far, and this is the number of new patents at that point. If you take logs, our beloved logarithms, and plot this thing into log-log scales, you get a surprisingly straight line that you can write like in this form. This is interesting. This is interesting. I find this by its own interesting, almost even disconnected from the whole discussion. I find this, that a process can grow like this, interesting. If you solve this equation analytically, you get this equation. And it tells you the following, that there are three types of growth that you can get from this equation. Sub-exponential growth if the exponent here is less than 1. exponential growth if the exponent is exactly equal than 1, or super exponential growth if the exponent is larger than 1. And remember that super exponential growth is partly interesting because it says that at a finite time, you get an infinite number. The system diverges. So which one is it? I mean, why would this growth be sub-exponential? One of the things that I'm going to do is you see these fluctuations here. So I'm going to take running windows of 50 years, and I'm going to measure the slope in those running 50 windows, and I get this timeline of the exponent. One of the interesting things here is that there are these epochs. There was an initial epoch of sub-exponential growth. There was then this epoch of super exponential growth, and you only get exponential growth like instantaneously because you have to cross the line, but you don't stay there. Then you have a large period of exponential growth again, and then we're starting, these are the breaking points, like since 1960 more or less, a period of super exponential growth. So we have this challenge. How is this consistent with our picture of collective learning? How can a collective learning process account for the approximately sub-exponential growth, but as well as the existence of these other regimes? There are many models that have been put forward to understand technological accumulation. One of them was by Weizmann, that he made your point. The paper is called Recombinant Growth. He said, the constraints are not on the number of ideas that we can come up with, is the efficiency at which we can process them. But in his model, he had to get to that conclusion because his model, which was very influential, predicted super exponential growth. Right? If you're recombining things, then your bag of technologies explode very quickly. Here we're not seeing that. So I'm gonna be bold and try to create my own model. And my own model is very simple. You start with your bag of patents. You're gonna understand why I'm highlighting some of the patents inside a subset. And I'm gonna say that subset is the only subset that can recombine with the rest. So you get these recombinations here with the rest of the set, which leads you to have what you had before plus the new recombinations. And that gives you this strange shape, right? That this is now in the new time step what you have now. And then you start the process again. But again, what I'm going to suppose in my process is that only the new ones are the ones that can be recombined. So only these can recombine. You don't recombine infinitely. So you get this. And you can model that with this equation. You can put some other parameters to assume that not even all the recombinations here are possible. You can say that patents become obsolete, so you don't recombine with all patents. And all those things just translate into multiplying by a constant here. This is just in words. And you can create the continuous version of that model for mathematical convenience, and you get this equation. You get this equation here, that the change in the new patents from year to year is given by this function. It's a function of the new patents that entered plus the patents that were there before, that were the old ones. Now I want to solve this equation analytically, and I get this functional form, which I find completely surprising. A tangent. So I would call this not exponential growth, not super exponential growth, it's tangent growth. Tangent growth is, for me, what the signature of a technological process, a process of technological accumulation. But I'm half kidding. So in the sense that this is the simplest model I could come up with. And but again, the challenge is how well this explains data. This has 3 parameters. Right? There's just one parameter here, C, but when you integrate, two other parameters come up. So at the end, this is a 3-parameter equation. And it predicts this type of thing, that time here starts at 0 and ends at and then so you can calculate what the critical time here to get to get to the asymptote. And when you fit the data to an equally complex model of 3 parameters, a polynomial, which actually this is also consistent with what we found with the when we were studying unit roots. This is also the fact that we found that unit roots were that the stationary was found when you took twice difference means that you have this cubic series, and if you fit those 2 models, you get that the tangent growth does a better fit. Does a better fit, and it predicts Simon that the singularity mind will be in 2051. Anyway, I mean, I don't think this is too relevant. There are other aspects of this work that we've been trying to study. It's also, these things accumulate in space, so these competencies to patent, we know appear in cities and agglomerate spatially. So that's another aspect that we want to understand. I'm not going to show you that work. So you can have the 3 regimes in a single model. So that, I find that interesting, but that also is disappointing in the sense that, well, it does seem that collective learning wouldn't have a specific signal that would show up as one of these 3 types of growth. Which leads me to the following hypothesis, and I'm not sure if this is interesting to you. Maybe it is the sequence in which they happen that it's interesting. You need to go through a process of first sub-exponential, then exponential, and finally super exponential. Maybe, I don't know. This is, of course, one of the weaknesses of this analysis, that we're looking these things at a very aggregate level, as you said, and it would be worth, obviously, to look down in more detail. But this is what I wanted to present to you today, and I really appreciate your comments, your criticisms, your different points of view. Thank you.